Hello everyone, this is a video lesson on uniform circular motion. In our previous lessons, we learned that an object must be moving in a uniform motion if it's moving in a constant speed and on a straight path, meaning there must be no change in its speed and direction. But for a uniform circular motion, we can say that an object is moving in a uniform circular motion if it is moving along a circular path in which there's no change in speed, meaning there's a constant speed, but its direction is constantly changing since it's moving in a circle. For this uniform circular motion, we can also say that it has a constant velocity which is tangent to its path. We also have to note that in a circular motion, there is a constant force acting on that object that is directed towards the center. As you can see here, Fc represents the force that is applied on this object, which is directed towards this center point. Now the question is there an outward force? If we have an inward force, is there an outward force on the object or this ball? Now, the question of an outward force can be resolved by asking what happens when the string breaks. Now the ball moves out or moves tangent to the path, not outward, as is might be expected. So it's not like this, so it's the wrong way. So the ball is moving this way. Okay, now let's say for example the central force is removed. So let's say we cut this, let's say it's a string. If we cut the string, so the ball continues in a straight path. So it will continue this way, not this way. Okay, so the centripetal force is needed to change the direction. Now, since the ball is moving this way and not this way, we need this. So this is what we call the centripetal force. It is the force that is applied by, let's say, the string. So, and it keeps the ball moving in a circle and not on a straight path like this. Now let me give you some examples of centripetal force. So for instance, you are riding a car which is going or moving on a curved path, and you are sitting on the seat next to the outside door here. Now, what is the direction of the resultant force on you as you turn? Is it away from the center or towards the center of the turn? Now the answer for that is the force on you is towards the center. It's always towards the center. And again, that inward force is exerted by the door on you. Again, it's centrally or directed towards the center. As you can see here, it's Fc or centripetal force, which is directed inwards or towards the center of the circle. Okay. Now, if you were asking if there is an outward force, yes, there is an outward force, but it does not act on you. It is the reaction force exerted by you on the door, and it affects only the door and not you. Okay, so this follows the third law of motion, which we will discuss in our next lessons. So as you apply, or as the door applies a force on you, in return, you are applying the same amount of force that is equal but opposite in direction of that force on the door. Another example is the spin cycle of a washer. Now let me give you this question. How is the water removed from the clothes during the spin cycle of a washer? Does the centripetal force throw the water off the clothes? Now think carefully before answering. Try to pause this video while thinking of the answer and go back to check whether your answer is correct or not. The answer to this question is no. Actually, it is the lack of force that allows the water to leave the clothes through holes in the circular wall of the rotating washer, and it's not the centripetal force that makes the water leave or be thrown off the clothes. Now we define centripetal acceleration as the quotient of the square of v, which is the speed, okay, and then the radius of the circle. And we know that the centripetal acceleration is directed towards the center. Okay, towards the center. This is because the centripetal force is directed towards the center, therefore the acceleration will be also directed towards the center. Now we can calculate the centripetal force, or Fc, as the product of the mass of the object and its centripetal acceleration. And again, so centripetal acceleration is v squared over r, we multiplied by m, so for us to get the centripetal force. Now let's use those equations in this problem. So example number 1, a 3 kilogram rock swings in a radius of 5 meters. If its constant speed is 8 meters per second, what is the centripetal acceleration? Now again, centripetal acceleration is defined as AC is equal to v squared over r. And we already know the v, which is 8 meters per second. So of course you have to square this, and we divide it by the radius, which is 5 meters. That is equal to 12.8 meters per second square. So this is the centripetal acceleration. And of course, if you are interested to know the centripetal force, we just have to multiply 3 kilograms and then the acceleration, which is 12.8 meters per second square, that would be equal to 38.4 newtons. Okay, so this is the centripetal force and the centripetal acceleration. Another example, a skater moves 15 meters per second in a circle of a radius 30 meters, and the ice exerts a central force of 50 newtons. Now the question is, what is the mass of the skater? Now again, we know Fc is equal to m times v squared over r. Now we are looking for the m, or the mass of the object. Now we can derive m, so m is equal to Fc times the r divided by v squared. Okay, and that would be equal to, so our Fc is equal to 450 newtons times the radius, which is 30 meters, divided by 15 meters per second square. And again, we have to square that, so 15 meters per second square, and that would be equal to 60 kilograms. Okay, so the skater is 60 kilograms. For the third example, the wall exerts a 600 Newton force on an 80 kilogram person moving at 4 meters per second on a circular platform. Now, what is the radius of the circular path? Again, we will use the same equation, so Fc is equal to mv squared over r. So now we are looking for r, therefore r is equal to mv squared over f. Now we're given with the 600 Newton force, 80 kilograms, so 80 kilogram, which is mass, multiplied with 4 meters per second. Again, we have to square this, divided by the 600 Newton force. That would be equal to 2.13 meters. Now, if a car is having a flat turn, meaning it is moving in a circle on a circular path on a flat surface, and the radius of the circle is r, now what is the direction of the force on the car? Of course, it is directed towards the center. So now here is the direction of the force. So this is the centripetal force, which is Fc, and this central force is exerted by the road on the car. So as you can see here, so the centripetal force is produced by the friction, or the frictional force, between the road and the wheels of the car. Without the friction, the car will continue moving on a straight path. Now, if we have an inward force, or what we call the centripetal force that is acting on the car, is there also an outward force acting on the car? Now again, there is no outward force acting on the car. It is only inward force. There is outward force, but it's the force applied by the car on the road, but not on the car itself. So again, there is only inward force. There is no outward force. Now, the nature of this central force is static friction. So again, what produces this inward force is the static friction. So therefore, Fc, or the centripetal force, is equal to the static friction S. Note that these two forces are not two different forces that are equal. They are the same forces. Okay, this is just one force. Now, this central force is exerted by the road, on the car. Now, in problems involving objects that are moving on a circular motion, and if we want to know or to calculate the maximum speed for the turn without slipping, now we have to note that if the object is on the verge of slipping, the Fc is equal to the force, or the static friction, or the static friction force, which is Fs. And we can say that Fc is equal to mv squared based on the equation that we have discussed earlier, and also Fs is equal to mu times mg, or mus, or the coefficient of friction, and then mass times gravity, or the acceleration due to gravity. Then we can say that mv squared divided by r is equal to mu s, or the coefficient of friction, times m times g. Now we can cancel, of course, m, and then we can calculate for the velocity, which is v. It's equal to the square root of, so we have the square root here since v is squared here. There is a square for v. That's why we have to get the square root. So v is equal to mu s times g times r. Okay, so this is the equation when we want to know the maximum speed for turn without slipping. Now let's apply that equation to solve this example problem number 4. A car negotiates a turn of radius of 70 meters when a coefficient of static friction is 0.7. Then what is the maximum speed to avoid slipping? Now again, we have an equation, so which is v squared, which is equal to mu s, or the coefficient of static friction, times g multiplied with the radius. So let's substitute the given values. Okay, so we have 0.7 and then multiplied with 9.8 meters per second square, and then we have r, which is 70 meters. Okay, and then of course we have v here, and we have square here, and then to eliminate that square we have to put a square root here. So that's equal to 21.91 meters per second. So this is our v, or the velocity. Okay, the maximum speed to avoid slipping. In many cases, cars do not just travel on a flat road. Now, bank curves were designed for drivers to drive their vehicles on the road safely. So for instance, this is a bank curve, so which means the road is angled from the horizontal at a certain angle. So if the car is moving at a slow speed, as you can observe here that the frictional force is directed towards this direction, so that it creates a balance with the weight, the normal force, and this frictional force, so that the car will remain on its path. While if the car is moving at a fast speed, this a frictional force is directed this way. And lastly, if the optimum speed is reached, so there will be zero frictional force. By banking a curve at the optimum angle, the normal force can provide necessary centripetal force without the need of the frictional force. Therefore, it's okay for us to have a zero frictional force here if we attain the optimum banking angle. If, for example, this is road is banked on an optimum angle, so of course the frictional force here, or the static friction, is equal to zero. So the acceleration A is towards the center, and we set the x-axis along the direction of the acceleration, which is horizontal left to right. So here the acceleration is going here, so that's the positive. Now if this is n, okay, which is the normal force, we can say that this is a force theta, and then this is also theta. This angle is equal to this angle, and again this is also theta. So to get the components of the normal force, we can say that this y component is equal to n cosine theta. So it's cosine since it's the adjacent side of this angle theta. Well, if you want to get this x component, okay, so this is n sine theta. It's sine theta since it's the opposite side of the angle theta. Now how do we solve for the optimum angle? So to solve for the optimum angle, we have to apply the Newton's second laws to x and y axis. So we can say that the summation of the components on the x-axis, or the component of the force on the x-axis, is equal to the mass times the centripetal acceleration. So that's equal to n sine theta. It's n sine theta since the only force on the on the x-axis is the x component of the normal force, which is n sine theta, and then it's equal to m times centripetal acceleration is equal to v squared over r. Okay. Now on the y component, and the y-axis, so that's fy, it's equal to 0. Okay, since the x component, or the y component of the normal force cancels with the weight of the object. So again, so we have n cosine theta, that's minus the weight, so we can just transfer that to the other side since it's just equal to 0. So that's mg, so which means n cosine theta, or the y component of the normal force, is equal to the weight of the object. Now we know that tan theta is equal to, so tangent is opposite over adjacent. So the opposite side of theta here is n sine theta, while the adjacent side is this, the y component, which is n cosine theta. Notice that our theta is measured with respect to the y-axis. That's why you might be wondering why it's y sine is on the top and cosine is at the bottom. So again, we measured theta with respect to the y-axis. So now our tan theta is equal to, again, let's substitute the values of this. So we have set here that n sine theta is equal to mv squared over r, so that's mv squared over r divided by, now n cosine theta is mg, so that's mg. Okay, so we can cancel m since it's just equal. Now we can say that tan theta is equal to v squared over r times g, or gr. And to get theta, okay, so theta is equal to r tan, okay, or the inverse of tan, tangent, and then v squared over g times r. So this is the equation for calculating the optimum angle. Again, for getting the optimum angle, we neglect the static friction. Now let's use that equation to solve this problem. A car negotiates a turn of radius 80 meters. What is the optimum banking angle for this curve if the speed is to be equal to 12 meters per second? Now again, we know that tangent theta is equal to v squared over g r. So therefore, our v here is this, so 12 meters per second divided by our g, which is 9.8 meters per second square, times the radius is 80 meters. So therefore tan is equal to, or tan theta is equal to 0.184. Okay, and then to get theta, that is arctan of this, so that's equal to 10.40 degrees. Okay, so that's the optimum angle or banking angle. Now, uniform circular motion doesn't only happen to horizontal circles, but it is also applicable for vertical circles. So for instance, this is a vertical circle which is centered at this point. Now consider the forces on a ball. So what if there's a ball that is tied, or that is attached to the center of this through a string, and it moves in a vertical loop? Okay, now note also that the positive direction is always along the acceleration, which is of course towards the center of the circle. And also note the changes in the position of the ball. Now here, if the ball is at the bottom of the circle, it experiences, or the string experiences, maximum tension, since this weight, the mg here, opposes the centripetal force. Now if the ball is here, the weight has no effect on the tension, since they are on different axes. So the weight is on the y-axis, while t here is on the x-axis. But if the ball is here, so the weight causes a small decrease in tension t. So since there is a portion or a component of t that is parallel with mg, that decreases the amount of tension on the string here, since it helps a bit on the centripetal force. But if the tension is on the top, or I mean the object is on the top, the tension is minimum, since the weight helps the centripetal force. Since both the weight of the object and the tension are directed downwards, they have the same direction, so the tension is at the minimum or the lowest value. Now at this point, okay, so it's on the left side again, since the weight is on the y-axis while the tension is on the x-axis, the weight has no effect on t again, so on at the bottom it's max. Now for instance, a force of 40 meters is required to maintain the circular motion of these balls. So here's of course to maintain the motion, the circular motion here, which is a weight of 10 newtons. So let's identify, or let's determine the amount of tension required at different positions, so at the top and at the bottom. Now at the top, so we can say that the value of tension is given by 10 newtons plus the tension, since they have the same direction, so that's why we have to add 10 newtons and t. 10 newtons is the weight of the object, while the tension is the weight or the force applied by the string on the ball. So this is equal to 40 which is the amount or the centripetal force required to maintain the circular motion. So for us to get T, so T is just equal to 40 newtons minus 10 newtons, that is equal to 30 newtons. So which means the tension required for this ball to maintain its motion or circular motion at the top will be 30 newtons. While at the bottom, so that is equal to T minus 10 newtons. So we have to subtract, since T is and 10 here is opposing the T, so that's why you have to subtract. They have different directions, so which is equal to, again, 40 newtons. Now the tension here is given by, so of course we have to transpose this N here, or 10 newtons here. That's why we have 40 plus 10, so that's equal to 50 newtons. So as you can see, the tension at the top is just 30 newtons, while the tension at the bottom is 50 newtons. So therefore, we can see here that the tension at the bottom is at the maximum value or bigger compared to the tension when the ball is at the top of the circle. So to generalize, so again, let's write Fc is equal to mv squared over r, which is the centripetal force. Now consider the top of the circle, which is this. That again, mg and t are directed downwards. So since they have the same direction, we can just simply add them. So mg plus t, that's equal to mv squared over r. Now to get the tension T, so we simply transpose mg to the other side. So that's mv squared over r minus mg. So this is how we get or calculate the tension when the object is on the top of the vertical circle. But if the object is on the bottom or at the bottom of the circle, so again, F is equal to mv squared over r. So at the bottom, so again, mg and t here, or the weight of the object and t, are at different directions. So we can subtract. So t minus mg is equal to mv squared over r. So to get t here, again, transpose mg to the other side. So that's t is equal to mv squared over r plus mg. So again, this is how we get t given mv and then r when the object is at the bottom of the vertical circle. Now assume that the centripetal force required to maintain a circular motion is 20. Then further assume that the weight is 5 newtons. So Fc is equal to mv squared over r, which is equal to 20. So this is the resultant central force at every point in the path, so which is 20 newtons. And the weight vector W is of course downward at every point, so even here, so the weight is always downwards. So the weight is equal to 5 newtons down. Now the resultant force is a vector sum of T and W at any point in the path. So at the top, T plus W is equal to Fc, so which gives us, so let me clear this out. So that's T plus, the weight is 5 newtons, which is equal to the centripetal force, which is 20 newtons. Therefore, T is equal to 15. So we have to transpose 5 to the other side. So that's 20 minus 5 is 15 newtons. So again, the tension at the top, if the centripetal force is 20 newtons and the weight is 5 newtons, so the tension at the top is 15 newtons. At the bottom, so T is equal to, or T, since again at the bottom the weight has opposite direction with the tension, so that therefore T minus W is equal to FC, so which is T minus 5 newtons is equal to 20 newtons. T is equal to, again, transpose 5 newtons to the other side, so that's 20 plus 5 newtons, that is 25 newtons. So again, the T, or the tension at the bottom, is always, or is larger than the tension at the top. So considering that, of course, this is a string. So let's say, for example, a 2 kilogram rock swings in a vertical circle of radius 80 meters, and the speed of the rock is constant at 10 meters per second. Now, what is the tension T in the rope at the top and the bottom of the circle? So we want to know the tension at this point, and at this point. Now remember, at the top, the direction of the weight and the tension T is the same. So therefore, we can say that weight plus T is equal to mv squared over r. So T is equal to, we can transpose weight to the other side, so it's mv squared over r, okay, minus weight, which is mg. Okay, so therefore we can say that T is equal to 2 kilograms times v square, so that's 10 meters per second square, divided by the radius, which is 8 meters, minus 2 kilograms times 9.8 meters per second square. Okay, so T is equal to 5.40 newtons. So this is the tension at the top. Now at the bottom, so again, T and weight, so weight is directed here, they are opposite, so T minus mg is equal to, so therefore T is equal to mg plus, okay, we just transpose this mg to this side, so plus mv squared over r, and that's equal to, T is equal to, m is again 2 kilograms. So anyways, it's just the same as this, okay, it's just the same as this, but we just change here, okay, we just change the sign here. So instead of minus, we just make it plus, so that becomes 44.6 newtons. Okay, as you can see, there's a big difference between the tension at the top and the tension at the bottom of the circle. Now, what is the critical speed at the top if the 2 kilogram mass is to continue in a circle of radius 8 meters? Now, let's say, for example, an object is moving, which is centered to this. So it's moving on a center, in a circle, on a vertical circle, and it's on the top of this, and the radius is equal to 8 meters here. Now, for us to get the critical speed, we should make the tension here 0. Okay, so T is equal to 0, which means we will cut this string, which allows the object to move at a certain velocity, or the critical speed Vc, so which is towards this direction. So this Vc is tangent to this circle here. Now, to get that, we can say that mg plus T, remember this is the equation that we used earlier, so it's equal to mv squared over over r. So if tension is 0, so this becomes 0, and of course we can also cancel m and then m here. This gives us an equation of g is equal to v squared over r. Okay, now to get v, so v is equal to, so just cross multiply g times r, so g r, but since we have a square here for v, now to get or to cancel that square, so you can just square root this. And substituting the values, so that's square root of 9.8 meters per second square times r, which is 8 meters. Okay, that gives us v is equal to 8.85 meters per second. So this is the critical speed. Now another example is a Ferris wheel. Now for a Ferris wheel, instead of using tension, so this is a hard metal, so we use N instead, or the normal force. So as you can see here, the normal force at the top, the normal force is in opposite direction with the mg. So therefore at the top, mg, okay, minus N is equal to mv squared over r. And then N, which is the normal force, is equal to mg minus mv squared over r. This is at the top. While at the bottom, as you can see, again, still N is in opposite direction as mg, but this time the positive direction, N has a positive direction since it's directed towards the center. So that gives us N minus mg is equal, so this is at the bottom, so N minus mg is equal to mv squared over r. So that gives us N is equal to mv squared over r, and then plus mg. Okay, this is how we calculate the normal force at the bottom and at the top of the Ferris wheel. Take note of this. So for example, what is the apparent weight of the 60 kilogram person as she moves through the highest point of the Ferris wheel when r is equal to 45 meters and the speed at that point is 6 meters per second? Now the apparent weight is equal to the normal force at the top. So since again we are calculating for the normal force, you can say that mg minus N, or the normal force, is equal to mv squared divided by r. So again, we are looking at the normal force at the top. So N is equal to mg minus mv squared over r. So substituting the values, N is equal to 60 kilograms times 9.8 meters per second square minus that's 60 kilograms also, 60 kilograms times v, which is 6 meters per second, divided by r, which is 45 meters, and that would be equal to 540 newtons. So this is the normal force at the top of the Ferris wheel, which is also equal to the apparent weight of the 60 kilogram person.